can act as bases. Okay? And ultimately that distinguishing feature between them is what they are acting or reacting with. So just as kind of a review there, your nucleophiles donate electrons, which is our standard definition. The part that's kind of extra to remember is that other than hydrogen. Okay, that's kind of an extra piece that I think is going to be particularly relevant. So if we looked at a nucleophile reacting with the substrate shown in the middle there, where would the nucleophile need to react? The nucleophile needs to react with that carbon, where our leaving group is attached. So there's going to be some kind of considerations to go with where that nucleophile has to go through an attack. What happens if we switch now to a base? Well, a base is a proton acceptor as far as we're concerned, because we go back and we said acids and bases, when I use them, are in reference to Bronsted-Lowry exclusively, because I'm lazy and I don't want to have to keep saying Bronsted-Lowry. Okay. If we focus on the electrons, our base is going to donate electrons specifically to hydrogen. Okay. So if we go back to our structure and we drew in our base, just like the nucleophile, is going to have a lone pair of electrons, and those electrons will share with our hydrogen. Okay. Both of these are going to result in effectively the same kind of thing happening in each situation, just like variations of them. So what we want to then consider is then how can we use those definitions to differentiate nucleophile versus base? Okay. And a lot of this comes down to what we're reacting with and where it is located. Okay. Both the base and the nucleophile will share electrons. It's now just what do they share with? Okay. If I want it to act as a nucleophile, that species that is sharing electrons, okay, it needs to share those electrons with something other than hydrogen. So carbon's our standard right now. Where is carbon in our structure? In the middle of the structure. It is buried behind a bunch of other stuff. What is that other stuff? Electrons. Well, what was our nucleophile? Electrons. So if there's a bunch of stuff, okay, on our substrate and a bunch of stuff on our nucleophile, what happens? They repel, which then means no reaction. We don't have a nucleophile, we don't have an electrophile because nothing happens. Okay. So if we want to increase the likelihood that I can get the nucleophilic reaction to occur, what characteristics need to come into play when we look at the nucleophile? It should be small. Okay. The bigger it is, the more likely it encounters other electron groups and it repels away from its reactive site. That becomes problematic. Okay, so our nucleophile in general needs to be small. If we now flip that on its head and look at the base, okay, what's the deal with the base? What is the base reacting with? Hydrogen. Where are the hydrogens located? On the outside of the structure. Does size matter? No. Completely irrelevant when we look at the base. Okay, size, really we don't care about at all. Okay, and that's because it's reacting with something really, really easy to gain access to. Okay, so our size, keep doing that, kind of irrelevant. Okay, but we can use this to help us predict something. Okay, let's say I use a species like, see if I can carefully unerase it, this guy. How would I expect that to react? More like a base or more like a nucleophile? Okay. Why did you say base? It's large. Okay, let's run with that. Nucleophile says I want small. Base says I want size irrelevant. So I don't quite understand what you guys are saying, because you're saying it's large, that's why it's a base.
It's large. So
it's not small. Okay. Yes, you're getting at the same idea, but you're using kind of the wrong approach to get to it. Okay. It's not that it's large, it's that it's not small. Okay. With it being not small, it's not a nucleophile. Okay? Since there's only two choices, that by definition then means it acts as a base. Okay? You had a hand, but you might have been saying the same thing. Okay, kind of makes sense? So we can pick and nail down our bases, and they tend to be large, which is really just the easy way of saying they aren't small. Okay? So the other big base that tends to float out there, if I can find it, there it is. Okay. I never remember its reference, but it's either dBu or dBn. They're both very similar structures. I believe one of them is a 6-membered ring as opposed to, what is that, a 7-membered ring? Okay. But they're both doing the same kind of thing. Where is the basic atom in that? Okay, nitrogen. Fair enough. But now you gotta get more specific. Which nitrogen? Why is the nitrogen with the pi bond, or our blue nitrogen, more basic than the red nitrogen? Resonance puts what charge on that blue nitrogen? A negative. Can we do resonance to put a negative charge on the red one? No. Okay. Which one's going to be more basic? The one that is negatively charged or the one that is neutral? Negative charge. Okay. Because it is nice and big and has tons of junk on the outside of it, that prevents it from getting into the inside of the structure. Kind of makes sense? What if we want it to act as a nucleophile? I see what you're saying. Let's run with an example. Give me an example nucleophile. Okay, that was a difficult one. Okay, so these were all bases. It's a good thing I organized it, right? Same sides. CN ends up being a nucleophile. Why is that a good nucleophile? It is small. Negatively charged, which makes it strong, okay, but that doesn't say base versus nucleophile. So small would start to suggest it's a good nucleophile. Okay, but remember, size is irrelevant. Can't that act as a base? It could, theoretically. What's going to limit its ability to act as a base? If it acts as a... Make you guys nervous over there? If it acts as a base, what happens? It forms HCN. What's going to affect its ability to act as a base? The reversibility of that reaction, which is referencing its Ka or its pKa. When we look up HCN, anybody know its pKa? Good, then I can make it up. I think it's somewhere in the 7 range. Okay. Relatively acidic. Okay, remember water is at a pKa of 15.7. We're looking at something that's relatively acidic here. Okay. If it's relatively acidic, it's not going to accept that proton. Did you just look it up? Yeah, 9.3. 9.3. Yeah, I wasn't too far off. With logarithmic scale, only 200 times. That's not bad. That's almost passing, isn't it? Okay. So defining that and understanding that, you'd have to have some pKa values memorized. This is why I said you should memorize your pKa's. Okay. There are some situations, okay, where we can get some good nucleophiles. If we go through and look at some common nucleophiles for organic chemistry, they've got a whole list of them in your textbook. Okay, we've got neutral ones. What's the issue with neutral ones? They aren't negatively charged, which then means they are weak nucleophiles. And the negatively charged ones are relatively strong. Okay. Within that, though, let's pull that very first example, which is the one I was hoping you guys would give me as an example for a nucleophile, OH minus. Nice and small, right? Great as a nucleophile. It is also a really good base. And this is one of the issues that pops up between nucleophiles and bases. Is if you have a negatively charged species, it can act very typically as a nucleophile and as a base. Kind of depends on the circumstances you're putting it in. Hydroxide, OH minus, is kind of our stereotypical awful choice as a reagent because it'll act as both the nucleophile and the base. And if it acts as the nucleophile, I see substitution reactions. If it acts as a base, I see elimination reactions. So hydroxide is nasty as a reagent because we get all sorts of different things happening there. So typically when we go through and look at our reagents, we want to pick species that will act exclusively as a base or exclusively as a nucleophile. Crossover reagents become problematic. Okay? So in the case of acting exclusively as a base, what did we decide? Size is irrelevant, sort of. Not small. Okay? So our base we want to be not small. As long as it's not small, it can't act as a nucleophile, which then means it'll act exclusively as a base. So we tend to want big things, and we've got a base. Okay, so that can be nice. We can now selectively push for our bases. But how can we selectively push for our nucleophiles? Well, it turns out a good nucleophile, okay, are halides. They will only act as nucleophiles. They will never act as bases. And the question I asked in the video was why? What happens if our halide acts as a base? It becomes HI. And HI is a strong acid that by definition completely dissociates. Okay? Which then means can't act as a base. Okay? So our halides tend to be very good in that respect. They'll act only as our nucleophiles. Okay? So acid-base chemistry plays a very important role in predicting nucleophiles and bases. Questions about that? Okay. So the rest of the slides that I kind of want to get through, which theoretically we'll move through in 15 minutes, are just summary slides. Okay? So SN1 reactions, you've seen this slide already. It's got our general mechanism all the way through it. Interesting features that pop up within this. Number one, when we look at the rate expression, okay, there's only one thing in it. Why is there only one thing in it? If we look at our rate limiting step, which is that first step, there's only one reactant, which means it is unimolecular. So it is referencing that rate determining step. Okay. What else is kind of interesting within this mechanism? What's going on in that purple box? We have an acid-base reaction. Okay. We don't see that acid-base reaction in our SN2 reaction, so it seems a little bit odd that we're throwing that in here. Okay. You'll also notice that if we look at our nucleophile, the nucleophile is neutral, meaning weak. Okay. But don't I need a nucleophile to do the substitution reaction? Yeah, so why am I looking at a weak nucleophile and still allowing this reaction to occur? The strength of the nucleophile is completely irrelevant to the rate of the reaction. It's only based on the substrate. That means don't put a strong nucleophile in there, put in a weak one. Okay. The issue with it being weak is it's not charged typically, and if it's not charged, it needs to somehow be neutralized by something else. The only way it can be neutralized is by something that is easy enough to add or remove from a structure, like an acidic hydrogen. So when we're running our SN1 mechanisms, you will very typically see this extra acid-base step to neutralize your nucleophile after it's done its substitution. Okay. Not always. Depends on the nucleophile, okay? But you will typically see that. Yes?
What happens if you put a strong
So then a question becomes is what happens if you now change the strength of the nucleophile, okay? Which is an important question, and we'll kind of address that a little bit later on. Okay. Solvent effects. What do we want with our solvent? Everything has to do with this first step. The faster I make that step, the more likely this reaction occurs. Can the solvent have an effect on either of those reagents? Yes. The solvent can stabilize the carbocation. If the carbocation becomes stable, what happens to the rate? It goes faster. So I want a solvent to stabilize a positive charge. That means the solvent needs to contribute a negative charge. Okay? I can't be formally negative and be a solvent as far as we're concerned for this class. Okay? So I need the largest partial negative possible. How do I get a very large partial negative? Okay? I need an electronegative element attached to a much less electronegative element. Okay? Our most electronegative elements being fluorine, oxygen, and nitrogen, and our least electronegative being hydrogen. So if I use those 4 atoms, I'm looking at a protic solvent, a hydrogen bonding solvent. So a hydrogen bonding solvent becomes great for the SN1 mechanism because it can stabilize that carbocation. Okay. Nucleophile was a relevant leaving group. As I talked about in the video, how much do we care about the leaving group? Pretty much don't care about it at all. Okay? And it's not because it's not involved in an SN1. It is involved. Okay? It is critical to have a good leaving group. Otherwise, the reaction can't occur. But it's critical for an SN2. It's critical for an E1. It's critical for an E2. The leaving group needs to be there, period. So evaluating the leaving group ability beyond just saying, is it good, is kind of irrelevant. Okay? The leaving group isn't going to help us push one mechanism versus another. So in our big summary, substrate. Biggest thing you should be thinking about in SN1, stable carbocation. Can I form a stable carbocation? Leaving group needs to be good. Nucleophile should be weak. Solvent, polar protic. The next big part are kind of some complications that come out of this. Stereochemistry. Okay? We have a loss of stereochemistry. Okay? Meaning we end up with 2 products, a racemic mixture, because our carbocation has 2 lobes, which means your nucleophile can attack from either side. We're going to end up losing our stereochemistry, quote unquote. Okay. How else can we reference that? Optical activity. We would expect no optical activity in an SN1 product. Okay. Complications. We form a carbocation. The instant you see a carbocation, rearrange it. Okay. At this stage, probably if you're working on homework up to midnight tonight, if you see a carbocation, do a rearrangement. I don't care if it's good or not. Do the rearrangement, prove that it's bad, and then you can say go back to your original structure. Starting tomorrow up to the exam, if you think it's bad, don't draw it. Okay? But at this point, you should be still practicing the wrong thing. Okay? Prove to yourself that it's wrong. Yes?
I had a question for the product. Is there ever a concern that solvent can donate a hydrogen to the carbocation?
You want to try that again?
Maybe. So I asked so
There's a protic solvent, right?
yeah.
And your question was what?
Could that polar product solvent possibly donate a hydrogen instead of to the yes?
What's the charge on the carbocation?
Oh, I don't know what I'm thinking.
It's okay.
I'm not thinking that's
It's a carbocation, which is positive. Your hydrogen is partially positive. So will it donate a hydrogen? No, but conversely, we do have a partial negative on the solvent, which could donate an electron. Typically, when you look at your SN1 reactions, it is very often that you won't see a solvent. Right? You'll only see a nucleophile. What is the nucleophile? It's acting as your solvent as well. Okay? So under most kind of SN1 reactions, your solvent is very, very typically the nucleophile, and that's why it's a weak nucleophile, because we have that acidic hydrogen attached to it. Okay? So important distinction to look at, can the solvent react? Yes. Don't start shuttling hydrogens around. Okay?
I don't know what else.
No, it's simple. What you were thinking was moving atoms. Okay? Everybody is going to be in a moving atom phase right now. Okay? Probably halfway through second semester, you'll stop moving atoms because you'll get yelled at long enough that you'll stop doing it. Okay? And even then, you'll probably start doing it in the last quarter of the semester just because you think it's irritating or funny to watch me get irritated. Okay? At this stage, you're in that crossover between moving atoms and moving electrons. Okay? It's very easy to get confused. When in doubt, go back to your atoms. Don't add any curved arrows. Just look at your bond and say, okay, which atom is more electronegative? Oxygen or hydrogen? Oxygen, which means the oxygen is partially negative, the hydrogen is partially positive. With the charges identified on your structure, if you now try and do a hydrogen to that positive there, you're now going to start to say, isn't that a little weird? Can I do positive to positive? Which is exactly what we're going for. Identify those partial charges. It will help you go through and run your reactions. Okay, particularly at this stage. Find the most positive, find the most negative, and connect them. You have your answer. Okay? So, in your complications, watch out for the loss of stereochemistry and watch out for rearrangements. Those are the two big ones. When we move to the SN2, we have again got our drawing set up. Our rate expression becomes a little bit different here. With only one step, both the substrate and the nucleophile will be involved, which means we have a bimolecular reaction. The bi in reference to the 2 in our SN2 reaction. So now the nucleophile does become important. Okay, so what's going to cause this reaction to go faster? Having a less reactive nucleophile or a more reactive nucleophile? More reactive. So now it's important, I want that nucleophile to be as strong as possible. How do I make it more strong? Make it more negative. Okay. The more negative it becomes, the more likely it'll act as a nucleophile and it can push this reaction. Okay. When we go through and look at, again, the same basic pieces, actually before we even do that, the next big thing I want you to remember, backside attack. Okay. Super, super, super important, and you don't need to repeat it, Corey. I don't even remember what it was, but you don't need to repeat that. Backside attack, you need to remember that. Okay. That's what drives the SN2 reaction. So when we look at our substrate, smaller is better. Why is smaller end up being better? Easier to get the nucleophile, which should be negative and small, to get in and react. Okay, so we want a smaller substrate. The leaving group, again, needs to be good, kind of irrelevant to our situation. Nucleophile needs to be strong. How do we know it's strong? You see a negative charge. Okay, and it should be small. Where's the negative charge? Okay, iodine. There's a reason we talked about bonds and their interactions. When we write out NaI, everybody goes, oh, there's no negative charge. That's an ionic bond. What you should immediately do when you see that compound is ignore the sodium and put the negative on the iodide. We now have a negative charge. Okay, that is a formal negative, strong nucleophile. Solvent. Okay. SN1, we wanted it to be protic, so it stabilized a carbocation. Is there a carbocation? No. Okay, so we can't use that as our reasoning. So why not the other extreme, our nonpolar solvent? What charge is our nucleophile? Negative. Is that going to dissolve in a nonpolar system? No. So nonpolar doesn't work. What if we just made it stupidly polar? That'll dissolve it. But then the stupidly polar has that proton, which can react with the negative, which does what to the negative? neutralizes it, making it non-reactive. That defeats the purpose of trying to run the reaction. So we can't use a polar product. We can't use nonpolar. The only thing left is polar aprotic. And that ends up being the solvent of best choice. Okay? Stereochemistry, so this gets back to our complications. What's our issue with our stereochemistry? We'll get inversion. Why do we get inversion? Backside attack. Okay? Do you always get inversion? No. We get inversion when we have a stereocenter. If there's no stereocenter, you can't have inversion. Okay? There are other kind of rare cases that pop up, but for the most part, okay, you will see an inversion in stereochemistry. The big benefit, no carbocation, which means no rearrangements. Okay? I know carbocations are nice to draw out. You can't draw them for an SN2. You want to show partial charges, that's fine. Okay? But no carbocations in the SN2.
I have a question.
Yep.
So when you see a nucleophile as a halide,
Mm-hmm.
does that most of the time always push to SN2? Since most halides are strong.
So, good question. If we see a halide, and you're asking between SN1 and SN2, presumably, right?
Yes.
Okay. Where are we going to go from there? Okay. Well, we have a strong one, so it could potentially push us immediately towards SN2. But what if the substrate is massive? Okay. If we have a massive substrate, can we do SN2? No. So what does that mean? SN1 starts to come into play. So there's now a dynamic on deciding between our mechanisms which one's best. Okay? So if we're just looking at substitution, this is kind of a bulk summary on how you should go through and look at it. You'll notice it's the same thing that we looked at in all the others. Substrate, nucleophile, leaving group, substrate pattern, solvents, and then kind of our results out of these. Okay? Put up in one big slide so that you can see all of those results. Okay? The two big ones that are going to become important are your substrate and nucleophile. Okay? Probably 80% of your questions come down to looking at the substrate or looking at the nucleophile strength on deciding which mechanism to run. After that, you very rarely see leaving group because they all need a good leaving group. Okay? So that doesn't help. Okay? I added this extra substrate pattern thing. Okay? I'm actually starting to get tempted to remove it, okay, because students will immediately go through and say, well, only tertiary or secondary, and they'll ignore everything else. What do I mean by ignore? We look at this structure up at the top. Can you see that up there? Good. What do you think that substrate? It's primary, so you might say SN2. There is resonance stabilization of the carbocation. If we attempted to pull an SN1 situation, we have resonance of that carbocation, which does what to it? Stabilizes it, which then makes it potential for SN1. So this substrate becomes a bit tricky because it can go either mechanism, SN1 or SN2. Yes?
Could you also see like maybe a rearrangement of a, not that particular carbocation, but of a different structure?
So as long as you can form the carbocation, you can see rearrangements. Okay? If you can't form the carbocation, you can't do the rearrangement. Okay? So in all cases, you must form that carbocation first, which is why when we look under the SN1 category, how many primary or zero areas are shown on my list? None, because I can't form them 99% of the time. Okay? What's a complication here? Secondary versus secondary. Does the substrate help you if you're a secondary structure? No, you have to find some other information. That's where looking at the nucleophile can come into play, or looking at the solvent. Okay? Again, the solvent is a dicey one, but it is distinctly different in each of those pathways. Okay? Once you've decided between SN1 or SN2, then you can look at your stereochemistry, you can evaluate rates. Okay? Did I do that all right? Yeah. Okay? You can think about your complications, all that kind of fun stuff. Make sense? Okay. I'm still hearing people ask about this question or ask about questions with rates, so I want to throw in one more piece of information that we've already talked about. Okay. In our rates, you notice that there are these brackets. What do those brackets mean?
Concentration.
Concentration. How do you calculate concentration? Okay. Moles over liter. What are the moles going to apply to? Whatever compound's there. Okay. So that's relatively straightforward. What do the liters apply to? The total solution. The total solution is primarily made up of the solvent. If I take those rate expressions and I change the solvent, does that have an effect on the rate? Yes. Not directly, because the solvent doesn't show up in the rate expression. And sorry, I don't know why that split lines. Okay. But it does show up indirectly in solving for the concentration. If we double the solvent, man, why does everybody have more fun than me? If our solvent doubles, what happens to the concentration? It cuts in half. Okay. So if running under an SN1 mechanism, I double the solvent, what happens to the rate? Slows down by exactly a half. Okay. So the solvent does still play an important role in deciding your rates. And that's only because it comes down to concentration in your rate expressions. Okay. After that, our elimination summary. Oh, there's a sneeze somewhere in there. Substrate, you're looking at stable carbocations. And where did we see that before? SN1. That's because the rate limiting step for the SN1 and the E1 is the same. Which then means if we suspect an SN1 reaction is going to happen, we're already kind of being upset because we have now two products. But it's now complicated because I could also see an E1 product come in there, and I could get split into 3 or more products depending on the complexity of my structures. So the one-type mechanisms are usually horrible as far as synthesis goes because we lose a lot of product yield. Leaving group, we still need a good leaving group. Nothing changes there. You'll notice here I don't say nucleophile. Okay? But you'll notice I am using the same color as the nucleophile. We now want a base. Why do we not want a nucleophile? We have a nucleophile, does substitution. That's the N of SN. Right? That's the problem. Right? So I want a base, potentially, because in that last step, what's happening? I'm forming a double bond, which kind of belies the chemistry that's happening there, because our double bond really doesn't actually form. We remove a hydrogen. Okay. So we've done, in that last step, merely an acid-base reaction. Okay. It's a little bit trickier than that, because we also form the double bond, so we can't call it strictly acid-base. We call it an elimination, but then we have to be more specific. What did we eliminate? We eliminated a hydrogen, and this is where I kind of disagree with the textbook in their naming system, but I kind of understand where they're going with it. We are eliminating a positively charged species. The general term for a positively charged species is an electrophile elimination. 9 times out of 10 when we're looking at our electrophile elimination, the electrophile in quotes is H+. It's a proton. Okay? But there are other cases where you could eliminate something else, which is why they're using the term electrophile elimination. It's a little bit sketchy, but that's where it's coming from. Okay? So we could potentially go through and use a base to do that, okay? But if we look at the SN or the E1 mechanism, what step of that reaction are we concerned about? The first step, again, the formation of the carbocation. Well, do I care about acid-base reactions in that first step? Nope. So do I want a strong base? Nope. Okay. So we're again focusing on that weak base. Okay. That last step is still not a particularly easy step to occur, okay, particularly if we don't add a base. Okay. We can help facilitate that reaction by adding heat. So heat can be a red flag, particularly if we're looking at SN1 versus E1. If you see heat being added, that can help push you over the edge to say, okay, it's an elimination reaction. Solvent, why polar protic? Stabilize the carbocation. It's still going back to those same patterns. Okay. Regiochemistry. Okay. In the SN1s, or the SN reactions, we looked at stereochemistry. Okay. Where's our chiral atom? Here we're going to refer to regiochemistry. Where is the formation of our double bond? Cis trans. We will see primarily trans because it's more stable. We can see some of the cis, and depending on the size of the groups in that cis arrangement, we can see a favoring one way or another. The larger those groups are, the less cis, the more trans. Okay? We come back to this naming everything. We get the Zaitsev product, which is our most stable alkene. Okay? That's what Zaitsev was referencing. Complications, you get tons of rearrangements as possibilities because of carbocation, which can do resonance, it can do hydride shifts, rearrangements, all that stuff. The other big complication is it directly competes with the SN1. Okay? Again, a big, big issue when we look at that reaction. E2, okay, our big defining feature between that, strong base. Okay, that's really the only thing that jumps out as being different. Right? And you might say, well, but in SN2, I wanted a smaller substrate. Okay? But what drives your elimination reactions? Zaitsev drives them, and what does Zaitsev want? The most stable double bond possible, which would then suggest tertiary substrates, because we generate a more substituted double bond. Okay? So we see a pretty big departure between SN2 and E2, and they're two different reactions, or they're two different styles. Big complication that comes down to this is actually kind of mentioned in our regiochemistry. It is dictated based on the alignment of the leaving group and the hydrogen. The leaving group and the hydrogen removed must be anti to each other. Okay? They add this extra term there, don't worry about it. Okay? But it's anti-periplanar for the elimination reaction to occur. Okay? So this can start to form less substituted products, okay, or anti-Zaitsev products, because of that anti-periplanar alignment, things that appear to go counter to Zaitsev. We'll talk about Hofmann much, much later in the semester, which is only like 3 weeks away, but we'll talk about it later. So don't stress about the Hofmann elimination now. Just like we did with the substitution, big old summary of everything on it. Okay. E1, you'll notice tertiary, secondary, just like the SN1. We won't see primary or zero area. For E2, you'll notice the tertiary is again the highest favored, just like the E1. It's higher favored because stable products. Okay? It's not like the SN2. You can still get eliminations. I shouldn't have put the zero area on there. Why can the zero area not act in an elimination? We need the other carbon to form the double bond. That was kind of a dumb thing to include in there. Okay. Solvent, do not evaluate the solvent when it comes to the E2 mechanism. Okay. It will lead you down the wrong path 9 times out of 10. Okay. For the E1, we do want the polar protic solvent. The rest of those are kind of general summaries. Questions?
What you said, don't evaluate the solvent for the E2?
Do not evaluate the solvent for the E2. And you can evaluate it for the E1 because it's following the same trend as the SN1. Okay. People actually copying this down, or can I advance? Okay. So the next thing to kind of do is how do we organize our thought between each of these mechanisms? Just like we did with NMR, we generate a table to kind of help us decide which mechanism to go through and do. Your textbook has gone through and come up with this neat little table that I think is a neat idea, except I have no idea what they're referencing. Okay? Their internal referencing of those terms just doesn't make sense. Strength? Strength of what? I don't know. Okay? What they're actually saying is strength of the nucleophile or base. Okay? I would argue that should not be the same line because substitution, I want strong nucleophile. Elimination, I want strong base. So if I can separate that into those terms, that'll make sense. Concentration, I think back to all of the reactions you've done. Where did it specify the concentration? It doesn't. Okay? What they're again trying to get out of concentration, okay, is strength. Okay? So they're pretty much duplicating themselves. Leaving group, yes, they included it, but look at how useful that was. Okay? Every single one of the mechanisms needs a leaving group. Solvent, we can go through and look at the solvent to predict between these. The idea would then be you total up at the end and say which one has the most check marks. In this case, SN2. So we say SN2 reaction. What would we predict our product to be? And then we could go through and balance out the rest of it, which you'll notice I very rarely, if ever, do, but we've got the NaCl. Okay. Here's my modified version of it. Okay. Wow, that looks a lot bigger than I thought it was. Sorry. I start with the nucleophile and base. In fact, I didn't order these very nicely. I would start my focus at the strong nucleophile or strong base. Okay. If it is a strong nucleophile, the check belongs in the SN2. Okay. If it is not strong, then SN1, no check in the SN2. Same kind of idea with the strong base. You'll notice that I have these not applicable marks because, well, in an elimination, it's not applicable. Okay? I don't want to look at the nucleophile. The leaving group I kept as a very tiny little font because it's not going to do anything useful for us. Substrate, solvent, and I've actually added heat as a column. Where would we expect to see heat? Favoring our eliminations. So if we go again back up to this reaction, we want to go through and think about this. Our nucleophile. First you got to identify it, okay? Which can be tricky because in our standard format, what you almost always see is substrate plus our, nucleophile goes to our product. Do I have to write it in that order? I can just as easily write nucleophile plus substrate goes to product. So don't focus on just because it's on the left side, it's the substrate. That order can change any way we want. So how do we decide which one's which?
Which one's more stable?
Break them both. See what happens. Chlorine, partially negative. Carbon, partially positive. Sodium, change that. Change that.
Just positive.
Just positive. It is formally positive. And the bromine, formally negative. We have a bunch of positives and negatives now. We have to address these. Which of those should we address first? The left or the right? I would argue the right is going to be the most important part to look at. Why should the right be the most important? It is formally charged. That is my highest energy species. That's where I want to keep my focus. Between those two, which one am I going to expect to react? The bromine, which means I can ignore the sodium. What have I now just identified? Which then means by definition the other species will be my substrate. I now need the nucleophile to somehow react with my substrate. That would exceed the octet. A lot of people have been drawing that first arrow and going, oh, it exceeds the octet, everything fails. So I got to show a carbocation. No, you don't. It's a reaction. In a reaction, are you allowed to break sigma bonds?
Yes.
Absolutely. Okay. So if we were just expected to predict a product, we might initially go through and do that. And we would say our product comes out to be I would say, okay, there's my answer. Is that good enough for an answer? How do you know that? I would argue you should check your multiple choice answers. If your multiple choice doesn't look at stereochemistry, do you need to worry about it? No. Okay? Maybe they're putting sodiums on there or something like that. You can simplify your work by taking a quick stab at what your possible product would be and then evaluate. Do I need to think harder? In this case, yeah, let's think harder. Okay? How should we go through and think harder? This is where you need to be evaluating something like this table. What kind of nucleophile do we have? Strong. Do I have a base? This was one of the things we just talked about. Bromide cannot act as a base. Okay? Which means there are actual hardcore zeros in those. Okay? That already starts me going, it's substitution, not elimination. Okay? Which could have helped me predict my possible product.
Would DMSO not be this base?
We'll look at DMSO in a second. Leaving group, okay, I would argue just not worry about it at all, but we could go through and mark it. Yes, there's a leaving group. Okay. Substrate. It's secondary. Secondary substrate means all of the above are valid. Solvent. DMSO. Okay. For the sake of this exam, if you don't recognize a shorthand like DMSO, you can raise your hand and ask. Worst case, I tell you no, I'm not going to tell you that. Okay. More than likely, I would tell you the structure for DMSO, and by tell you, I draw it up on the board. Those groups are known as methyls. There's the M. How many of them are there? Dimethyl. The sulfur oxide. I don't expect you to be able to break that down, but that's where it's coming from. Okay? When we look at that structure, what do you see? Protic or aprotic? Aprotic, which suggests SN2. We said to ignore the E2, E1 and SN1 both want protic, so that doesn't add to anything to them. Do we have heat? No. Nope. So go through in total, and we have 1, 2, 3, 4 versus 2 versus 2 and 2. Reaction is SN2. I now know the type of mechanism. Hey, cool, my arrow pushing was actually correct. That's nice. Okay. I now have to remember the complications of the SN2, which were stereochemistry, and I get inversion. If my leaving group was wedged, my new nucleophile must be, and I have my answer.
Could you provide one of the charts for the test and you could work it out?
I did not even consider that. Sure. I'll put it, I'll see how many I can squeeze onto a sheet of paper. Print a bunch of those as addendums. Not for the final, but I'll do it for this one.
I have a question. On the practice exam, you gave something like this, but it said that you wanted to do an SM1, but you didn't give a nucleophile or solvent. How will you do that one?
I'd have to see the practice exam. Do you remember what question? Or just, actually, it's not. And you're right. There's nothing written over that arrow saying a nucleophile or a solvent. Okay. Does that mean there's not a nucleophile? No. Okay. So let's just say for a second, we don't know what's going on with that. I am telling you SN1. So what does that mean? I need to form a carbocation. Okay, so I can go back to my structure and say, where would I form a carbocation? Well, oxygen's really electronegative, which would make that carbon positive. Okay. Bromine's really electronegative, which would make that carbon positive. Yeah? Okay, so now we say, okay, there are two places where I could form a carbocation. Is one better than the other?
Yes.
What are you using to decide which one is better than the other? Which one is the better leaving group? Bromine, being the better leaving group, should take the electrons in our first mechanistic step. Yeah? Okay. So you've now followed through, at least with SN1. If you now say, well, crap, I don't know where to go from there because you didn't give me a nucleophile, you're a horrible, evil person, fine. You've got partial credit because you've shown that you understand the first step of the SN1. Okay. And admittedly, this is a very difficult reaction for students to pick up on, which is why I added a bit of information here. Intramolecular means within. So I need to be looking at that molecule and saying something needs to happen within it. Well, what's the most reactive thing there? The carbocation. Exactly right. What do I need to stabilize that carbocation? Where are their electrons? Okay. And this is where people tend to freak out. Okay. And this is how I would go through and draw this. And nobody really likes my drawings, but I'm going to show you how I would do it anyway. One of those lone pairs is being used to make that bond. Okay. Because the oxygen just shared electrons, that oxygen is now formally positive. Does oxygen want to be positive? Nope. So what happens? It'll take the electrons away from the hydrogen, and I would end up with my final answer. I'd be like, peace, there it is, next question. Okay. How many people look at that and go, yeah, okay, I got that? Anybody look at it and go, why the hell would you draw something so freaking ugly? Nobody looks at it and just be like, okay. Some people say it's ugly, okay? Are you being graded on how pretty it looks? No, so don't worry about it. As long as it's correct, screw the grader. And that was recorded, even better. But that's really what you should evaluate. Do you have the correct drawing? Yes, move on. Okay. The next question becomes, you have time. Okay. Remember, the easier it is for the grader to finish grading, okay, the more likely you get points. If you now have time, you can go back to the structure and say, okay, well, really what's going on? I have 1, 2, 3, 4, 5 atoms in a ring. Well, I can draw a 5-membered ring relatively easily. There's my 5-membered ring. One of the atoms in it needs to be an oxygen with 2 lone pairs. Okay. Ooh, I also have this weird methyl group floating out there. I don't quite know where to put that, so I'm going to go through and number. I'll call the oxygen 1, 2, 3, 4, 5. I'm counting in a clockwise fashion. At position 5, I need to draw my methyl group. Okay. Now it looks a lot prettier. And I took more time to do it.
And you give yourself room for error by
Okay.
messing up that methyl.
And potentially increase the odds of doing error with where I drew the methyl group, okay, by drawing it prettier. Okay. I would highly encourage you to draw it ugly first. If you got time, then make it look pretty later. If you go immediately from straight line to pretty, more often than not, you will screw something up. Okay.
In this specific example, would it have mattered if you screwed up and put it on the 2? Because that's just the same thing if you rotated?
It wouldn't matter if I put it on the 5 or the 2, but the issue that I've noticed is that students will start to slide it out into the 4 and the 3 positions. Okay. Everybody happy with the answer up there? Say no.
And we don't need the peripheral stuff, or do we?
So peripheral stuff, the only thing you need to draw out is always organic materials. If it's not organic, don't worry about it. What's wrong with the structure? What did I start with? Stereochemistry. which means I need to be considering stereochemistry when I get to the product. Do I still have a chiral atom? Carbon number 5 is a chiral atom. Okay. Because this is an SN1 mechanism, what happens to the chirality? I lose it in the course of the reaction, which means 2 products, where one, that methyl is wedged, and one, that methyl is dashed. Okay. Why? Comes back to our ring closing reaction. That carbocation can be attacked either from above or below the plane, which causes the methyl group to kick one direction or the other. So we officially end up with 2 products. Okay. Some things to kind of watch out on that. I do kind of expect you guys to be able to come up with this, though this is kind of one of those bigger challenge questions because we never officially talked about it in class, and I've kind of held it off of the slides. The intramolecular was a tip-off because most students seem to screw up this reaction because they don't see the extra pieces. You're too focused on 2 separate things, and I got to react 2 separate things. Positive, negative, every single time. Okay? It'll get you through all the way to the answer. So within this answer, if you wanted to just draw one of them back to that time situation, you could just go through and say plus an antimer. Also perfectly valid.
Would it be better to avoid confusion by writing W slash or with? Because you might confuse the plus with the charge.
I don't think I would. It's not a bad idea, but I don't think I would. Okay. So when we go through and look at our reactions, or predicting our mechanisms, this is really what you're trying to process through. Some kind of grid matrix to help you decide which mechanism is going to be the ideal system. Okay? You should be doing that every single time you look at a substitution reaction. Even if you're told, say in the homework, do SN2, run through this. See if it actually should have been SN2. Okay? Prove to yourself one way or another. Questions about that? Okay. These next few are again just more summarizing things on deciding between the 2 mechanisms. Strength determines your order, 1 or 2. If it is strong, you're going in the number 2 situation. Okay. Between nucleophiles and bases, you have to watch out because they can kind of contaminate each other, or their definitions overlap. Okay. Your classic examples for nucleophiles, your halides. Your classic examples for bases, T-butoxide is your big one, DBN or DBU, whatever the hell it is. Okay. After that, substrate structure. Primary halides is kind of a nice one when you look at your substrate, because very typically if you see a primary halide, you're looking at an SN2. Okay. There is a small outside chance that it could be an E1, or an E2, sorry. Okay. But it's relatively limited. Secondary halides, life just sucks, stop looking at it. Okay? The secondary halide will do everything. You need to find something else to differentiate. Your tertiary halides, not much better than secondary, but it does at least eliminate the SN2. Okay? Solvent, your protic favors your SN1, aprotic SN2. I would in general kind of avoid conclusions about your elimination reactions. High temperatures favor elimination. Questions about any of that? Okay, there are officially 6 slides left in the lecture. Okay, what I'm going to do is just real quickly mention them. Acid-base mechanisms, okay, as bad. If we're in a strongly basic environment, what would be a bad thing to do as a first step? pH. That's getting me darn close to the final product, right? Right, that works out beautifully, except I have formed a positive charge in a solution that is negative. KOH is a strong base. Really what we're saying in that is negative, which means do not under any circumstances show a positive charge, which means that mechanism is now wrong. Right? Conversely, if we flipped over to the other situation, right, and I wanted to go through and do this reaction, right, I could potentially go through, it's actually going to go this, come on. Here's my pH. Right? Anything wrong with that? Well, I'm in an acidic environment. An acidic environment means there's a ton of positive. What is wrong with that structure? It's positive. What's the other structure? We had hydroxide as a leaving group, which number one is a problem in general. But hydroxide, okay, so bad reaction, bad reaction. Intramolecular bad versus good, right? If we go through and look at this intermediate, to get to our final product, what has to happen? We need a hydrogen here, and I need to lose a hydrogen over there, right? So one method, let's see, not drawn up there, so let's go back one, that I will see some students attempt to go through and do will be, oh, it just does this. Okay. That is an intramolecular protonation, deprotonation, general bad idea. Okay. So how would we go through and do that? It sucks, but you do it twice. You have your solvent pick up the hydrogen to produce product number one. And then you have your solvent with that hydrogen to get you to your final product. And what you would have drawn out in one step is now drawn out in two. It wasn't more efficient to draw one than two. Yes, but we are not working on efficiency. We are working on how is it going to work in the actual molecule. The molecule or the chemistry is likely going to break it into two steps as opposed to one. It is too difficult to get that hydrogen wrapped around to the oxygen to do that intramolecular reaction. Because what do we end up forming as an intermediate? In this case, we have a 5-membered ring. And 5-membered rings, while relatively stable, are not the most stable situation. Okay? So the odds that we would ever do that, not going to happen. Relatively limited, yes.
So if waters are solvent, could we still do it in one step with a lot of airs?
Nope. You try to do it in one step, then you're bringing in 2 water molecules to go through and do it.
Okay.
And that becomes problematic because you then have a termolecular reaction. 3 sums don't happen. Yes, successfully.
Also, as you form the intermediate ring, you exceed the...
So remember, yes, we will be exceeding the octet within that intermediate, but that's because electrons are shuttling around between it. What we're looking at is the transition state, the peak between our reactants and our products. So it never exists, which is why we can attempt to draw it. You will encounter reactions like this, which is fun because the only way this works is because it's done intramolecularly. Okay? The oxygen, in a sequence of steps, must attack that position. There's no other way to do it. Okay? So why is it okay to do it now but not in the other case? In the other case, we have evidence to suggest it doesn't happen. In this case, we have evidence to suggest it does happen. Sucks the way it works. Okay? Alkynes, elimination and substitution. If I want to go through and make an alkyne, I can add a stupidly strong base to a dihalide. The dihalide can be in either location, right? And that can take me down to the alkyne. Okay? It has to be a stupidly strong base. Why? It has nothing to do with the number of hydrogens. It's the pKa of our hydrogens, our substrates. Those are not easy hydrogens to remove from the structure. Okay? So that's why we have to use a really, really strong base. What is one of the nice things about generating this structure? Let's see, did I actually draw it? I didn't draw it. What is attached? A hydrogen in a stupidly acidic environment, what happens? And I can make what species? This is a couple things. What did I make? A negative carbon, which we said was stupidly difficult to do. This is one of the ways we can do it. Really helpful. Okay, another big reason, what can negative carbons do? Can act as a nucleophile, and we can grow our carbon structure because we now have carbon-carbon bonds forming. Okay? So we'll see that again at the end, towards the end of the semester. Intermolecular versus intracyclization reactions. This is just more on that same topic. When can we go through and do it? Right? Intermolecular reactions can go through and happen. So even with this substrate, which is similar to the one you saw in the exam, we can do an intermolecular reaction. Okay? And it generates this big, long, nasty-looking structure. Okay? Conversely, we could do it intra. Why would we see one reaction versus the other? Depends on the stability of the products. If we do an intramolecular reaction, we generate a neutral product. If we do inter, it's charged. Okay? So the stability of those individual products is why we end up seeing those come out. If we end up with a 7 or 8 membered ring, we start losing the ability to do an intra reaction. Okay, questions? Really? No questions?